All right, today is day one of section 5.4. We're learning a new set of formulas known as the sum difference formulas. What happens is we have a set of 6 formulas that can be expressed much more compactly as 3. What's going on here is the sign sum and the sign difference has the same structure, except for that is different in the middle. When that's a plus, that's a plus. When that's a minus, that's a minus. So these two formulas can be condensed to a single formula by using this notation. And that plus minus doesn't mean we do the problem twice or we take 2 different roots, which sometimes that's what the plus over minus notation indicates. In the context of these formulas, we read this as if that's a plus, that's a plus, if that's a minus, that's a minus. Now the cosine sum, cosine difference, again, the structures are almost identical. If that's a plus, that's a minus. If that's a minus, that's a plus. So the way we condense that into a single formula is that plus over minus, minus over plus, means that whatever this is, that's the opposite of. So if you're adding these two things, you subtract those. If you're subtracting those, you add these. Okay, tangent has a similar deal going on, where the top matches that, the bottom is the opposite. The top matches that, the bottom is the opposite. So the way that gets condensed to a single formula is whatever this orientation is, that's the same. If that's a plus, this is a plus. If that's a minus, that's a minus. Once you flip that, that means you're taking the opposite of whatever this is. Now similarly, as we discussed with other identities and other formulas, u could be a single variable, it could be a number, it could be an algebraic expression. And the same for v. U or v could be any one of those things. All right, now let's actually use these things. Okay, first emphasizing some algebraic structure here. You can't take a trig function and distribute among 2 angles. This and this are not the same thing. Well, how do we treat those? Well, sine of 135, you can simply evaluate that right off the unit circle. Sine of 30, you can evaluate it right off the unit circle. As far as condensing these down or simplifying them down, that's the best you can do as a single fraction. This one here, what we have going on is we're going to expand this out using the appropriate formula. So this is a sign difference. So the pattern for sine, sine, cosine, cosine, sine, sine, cosine, cosine, sine, that has the same orientation as that. If that's a minus, this is a minus. UV, UV. UV, UV, UV. Each one of these guys can be evaluated off the unit circle. Do so. Do your order of operations, that multiplication, and then the best you can do as far as a single fraction is to make that look like this. Now if you type this into your calculator, type this into your calculator, you see that there are 2 different decimal approximations. The moral of this little slide right here is this is not the same as that. Second moral of this is, okay, well, how do we expand that out using our new formula? Or set of formulas, the appropriate one of that set of 6 formulas. All right, so what are we going to be doing with these guys in terms of fitting this into the bigger picture of what we've learned so far? Next slide here, it's asking us to find the exact value of the cosine of 75 degrees. Well, 75 degrees does not appear on the unit circle. So prior to today, we would have no way to get an exact value of the cosine of 75 degrees. The best we would be able to do would be to get a decimal approximation in our calculator. One of the things this set of formulas allows us to do is if we can express an angle as a sum or difference of anything that appears in the unit circle, we can now get an exact value for it. So one way to rewrite 75 degrees with angles that appear in the unit circle is the 45 plus 30. So the cosine of 75 is the same thing as the cosine of 45 plus 30. So now what we need to do is choose the correct formula to expand that out. So we need the cosine sum formula. So if that's a plus, this is a minus. If that's a minus, that's a plus. Specifically this sum, that's a plus, this is a minus. So U is 45, V is 30. So they go in those slots right there. The trig function pattern is cosine, cosine, sine, sine. Each one of these guys gets evaluated from the unit circle. Order of operations, multiply, multiply, gets us to here. Getting that to a single fraction looks like this. Now that answer may kind of look familiar in terms of its overall, what it appears to be. You see here we got a root 6 plus root 2 over 4. Oops, sorry, didn't see that. Got a root 6 plus root 2 over 4. Here's a root 6 minus root 2 over 4. That tends to kind of be the flavor of what the answer looks like. There are only so many ways you can pair up the numbers on a unit circle in terms of getting these new values that we can get exact values for. So they kind of all, not all of them, but many of them tend to have variations of structures that look like that. Now I purposely started off with degrees for the example on this slide, examples in this one. Finding a sum or difference of two angles from the unit circle in degrees, most students are pretty good at. Visualizing that 75 is 45 plus 30 is not really a stretch. So I specifically started off with degrees because it was an easier way to introduce the topic. As you realize, degrees are very much a minority in terms of how we measure angles at this part of the course. So we have to be able to do this in radians as well. So we want the exact value of the tangent of pi over 12. That's our goal to get that. Well, pi over 12 does not appear on a unit circle. One of the things that these formulas allow us to do is if we can express that angle as a sum or difference of two angles that do appear in a unit circle, we can get an exact value for it. So, thinking about two angles in radians that add or subtract somehow to give you pi over 12, that can be tricky business. That's not easy to do. So for some of these guys, a good strategy may be, depending on your mental math skills with radians, is well, let's convert that over degrees. Finding the tangent of pi over 12 and finding the tangent of 15 degrees is the same thing. So if you're better at doing it in degrees, then do it in degrees. So one way to express 15 degrees is 60 minus 45. It's not the only way. We could go, for example, 45 minus 30 if we wanted to. A lot of these have multiple options of how you could pair up the angles. They'll ultimately all lead to the same final answer in the end. It's just a question of the path being a little bit different to get there. So if you decided to do this problem as 45 minus 30, you're going to get the same answer. As long as you pick two valid angles, you're okay. So that means we need the tangent difference formula. So the tangent difference formula is going to have this overall structure right there. Whatever this is, that's the same as. Whatever this is, that's the opposite of. The U for this problem is the 60, the V is the 45. So plugging in the right numbers here, the tangent of 60 minus the tangent of 45, 1 plus, oops, got a typo here, that's 60. 45. All right, well, there's only two of them. The tangent of 60, tangent of 45, they can be evaluated right off the unit circle. Plug those numbers into this formula. There's not a whole lot to do to get from this step to this step. 1 times root 3 is just root 3. Now, this is a numerical fraction. So although we've talked about algebraic fractions, it's acceptable to not rationalize denominators. If it's numerical, you're still expected to. So what you have to do here is multiply the top and bottom by 1 minus root 3. Like that. A basic radical evaluation like this is considered prerequisite knowledge. It's something you need to be able to do. I'm not going to go through the mechanics of multiplying that out. After you do multiply that out, it simplifies down to this. If you check it on the calculator, if you put your calculator in radian mode and do the tangent of pi over 12, you're going to get the decimal approximation of 2 minus root 3. All right, now what we're going to do is we are going to reverse the order of the question. And what I mean by that was we took something that, what's the best example here, looked like the cosine of 75 degrees, expanded it out to this, and then answered the question. Now what we're going to do is look at what if it's already expanded, can we condense it down? All right, here's a justification of why we might want to do this. Our ultimate goal is we want to evaluate this big expression right here. If 55 degrees and 10 degrees appeared on a unit circle, we could simply evaluate each one of these, do the order of operations, and write our final answer. They don't. So what if we rewrite this using the appropriate formula? Okay, sine, cosine, cosine, sine, sine, cosine, cosine, sine. This corresponds to the sine version. And then specifically, these guys have the same SIGN. So if that's a minus, that's a minus. So this thing is the same as the sine of 55 minus 10, or the sine of 45 degrees. That number comes right off the unit circle. Okay, a radian version. Again, one option we could look for. Our ultimate goal is we want an evaluation for this entire expression. One thing that you could do is check to see if these numbers appear in a unit circle. If they do, you could evaluate each one of those four guys, do your order of operations, write your final answer. Okay, they don't. So, can this thing be condensed using one of these formulas? Cosine, cosine, sine, sine. Cosine, cosine, sine, sine. This has a cosine pattern to it. And specifically, those guys are opposites. So it's the cosine of the sum, and then the sum of those two angles. So pi over 9 plus pi over 18. Okay, that's basic fractional computation. We've been doing it for a while. I'm not going over that on this slide. Add those together, take the cosine of that answer, evaluate it off the unit circle. Okay, a tangent version. It's hard to confuse tangent with anything else. Just verifying that the structure is there. Tangent, tangent, 1, tangent, 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 1, tangent, tangent. The tops need to match, bottom opposites. They're opposites of each other. That's a minus, this is a plus. Everything seems to fit together. Oop, something. Do we have another typo on this slide here? Okay, this is minus plus, so this should be a minus. Okay, let's just confirm this to see if that's the only typo or not. So giving them a common denominator of 12. So this will be times 3. So it's 15 pi over 12 minus pi over 12, 14 pi over 12, 7 pi over 6. Yeah, so that should have been a minus. Minor typo on that one. All right, next slide. What we're going to do is take this numerical version and make it algebraic. Again, the u's and v's could be individual angle values, like pi over 9, pi over 18. They could be variables like x and y, or they could be algebraic expressions, which brings us to this right here. So, sine, cosine, cosine, sine. That fits the sine pattern here. Whatever this is, same there. So this is going to be the sine of two things being subtracted, 5x minus 6x, negative x, sine of negative x is c. Okay. Cosine, cosine, sine, sine. Cosine, cosine, sine, sine. That has a cosine pattern to it. Here, those guys are opposites. So if that's a plus, this is a minus. 4 theta minus 6 theta, negative 2 theta, cosine of negative 2 theta. Oops, I guess we need to keep this in here so we can compare it to that. Okay, clearly this is a tangent. The top SIGNs are the same, bottom are opposites of each other. So this is going to be the tangent of, same as that, 5 theta minus 4 theta is 1 theta, tangent of theta. All right, this one, we've already done one of each, a sine, a cosine, a tangent. I'm going to skip number 4 in the interest of time for this video. All right, a connection back to one of the sets of identities we introduced A151, our cofunction identities. Okay, these were our 6 cofunction identities. We haven't done a whole lot with them in the last couple classes. What we can do with the sum difference formulas is verify some of these guys. So I'm not going to do them all. We're just going to do the first one right here. We're going to verify that the sine of pi over 2 minus u does equal the cosine of u, and we're going to do it with the appropriate sum difference formula. So this is the sine difference formula. So that's our u, that's our v. So the u is actually in the v slot. And there's nothing magical about u and v. It could be x and y, it could be smiley face, sad face. It's the algebraic structure that's important. So it's going to be the sine of the first, cosine of the second, cosine of the first, sine of the first. Sine of the second, rather. For sine, whatever that is, that's the same. Okay, this can be evaluated. Right off the unit circle, sine of pi over 2 is 1. This can be evaluated. Cosine of pi over 2 off the unit circle is 0. Well, 0 times anything is 0. 1 times cosine of u is cosine of u. Cosine of u equals cosine of u. All right, that is it as far as what we are covering with the sum difference formulas for today. We're going to be spending a couple more days working on these guys, and each day we'll look at different applications, excuse me, what you can and can't do with these formulas, but that is it for today in terms of what we're covering.